Okay, section 14.3 is about series. So in the last sections we talked about sequences, and sequences and series are very, very similar. And they always get looked at in conjunction with one another. So we have two things to talk about in this section. The first is to look at identifying series, and using summation notation. And our second thing that we're going to talk about is finding partial sums of series. So, because sequences and series are so very similar, I like to start this section by comparing the two. This is just going to be a little comparison of the properties that we know from sequences versus the properties for series. So the first thing is a sequence is just a list. These are lists of numbers like 5, 9, 13, and some brackets like that, maybe longer. Whereas series are sums. They're big addition problems. So we would have 5 plus 9 plus 13. So that's their biggest difference. Sequences we know can be finite or infinite. And series can also be finite or infinite. Sequence has a general term a sub n. A series has a general term of a sub n. Now, because series are summations, they get a special notation called summation notation. So the summation is capital sigma equals 1 goes here, k goes here, and the general term a sub n goes here. So we're going to dive into this summation notation in a little bit more detail here in a second, but you already heard me do it once. It's really easy to confuse sequences and series because they're so very similar. Just know that when we're talking about the series, we're talking about the summation of the terms, and when we're talking about the sequence, we're talking about the list of the terms. But they're both represented by a sub n and a sub n. So when you have a sequence a sub n, you're just listing what those terms are. When you have a series of a sub n's, you are adding up all of those terms. And that's the big difference that we need to make sure we key in on. So let's talk about our summation notation. So we're just going to rewrite here I equals 1, k, a sub n. So we want to break down what each of these pieces are. So this is the Greek capital letter sigma. This is the sum of whatever comes after it. What the I equals 1 is the index. And this tells us where we start. And the k is the top of the index. This tells us where the sum ends. this summation can be read as the sum from I equals 1 to k of a sub n. That's how we would read that. Mathematically, what this means is we start at 1, we have a1 plus a2 plus a3 plus dot 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 until we get to ak. And that's what our series is this big summation. And so because k can be a number, and it will be a number, if k is 50, we don't want to write 50 things. So we have this nice notation to keep it short and sweet. Now the I, the index, this can be a lot of different things. It can be I, common ones that we also see could be k, j, l, m, n, r. We don't typically use x, y, or z, or a, b, or c for the index. Now, is that a hard and fast rule? No, because it's just an index number. It's a counting number, right? Counts up 1 up to the k value. So our standard form is the S of n that I had above. So that's S of n equals sum from I equals 1 to n a sub n. And what this is the nth partial sum. So you can change your n, and that tells you what to change. And the reason we use the standard form here with the partial sums is because we can't have infinite series. So since we can see infinite series, I equals 1 to infinity of a sub n. So we use the partial sum notation a lot of times when we're talking about infinite series because we don't want to add up infinite things. So before we dive too far into partial sums, let's go ahead and just play around with evaluating some series. So let's start with classic question that you'll see a lot in the homework. Evaluate the given series. So in part A, we're going to have the sum from I equals 0 to 6, I minus 2 over 2. So we're just setting up just like we did up here, from 1 up to k. Now this one starts at 0. It can start at whatever number you're told to start at. Traditionally, we start at 1, but not always. So we have 0 minus 2 over 2, plus 1 minus 2 over 2, plus 2 minus 2 over 2, plus 3 minus 2 over 2, plus 4 minus 2 over 2, plus 5 minus 2 over 2, plus 6 minus 2 over 2. And we would just add all these up. And when you add all these up, you end up at 7 over 2. And that's the evaluation. So I said that we could start at any number. So in part B, we're going to evaluate the sum from n equals 4 to 7 of n squared. 4 doesn't quite look like a 4. So now we're going to start at 4. We're going to keep changing n until we get to 7. So this is 4 squared plus 5 squared plus 6 squared plus 7 squared. And when that's all added up, we get 126. So you can see when we're adding these things up, there's not a fast way to do this. There's just adding up every term that we're given. So a lot of times when we're told to add things up, we don't talk about it like this. We would call this the sixth partial sum. So that's where the partial sum comes in. So we can talk about this partial sum as the fourth partial sum or the sixth partial sum. Tongue twister there. And so, oh, I got enough space here down at the bottom. So when we're told to find the nth partial sum, it means find the sum of the first n terms. So the nice thing is, unless you're told otherwise, we assume that the partial sum starts at 1. So let's say, for an example, we're told to find the nth partial sum, and we're going to find the fourth partial sum. A sub n equals 2 plus 3n over n squared. So if you're not told otherwise, we're finding S4, and we're going to assume that n starts at 1 and goes up to 4. Unless you're told otherwise, you get to assume that. So if it says where n starts at 0, or where n starts at 3, or for even n's, if there's a restriction, then you make sure that you satisfy that restriction. But if they just give you this kind of problem, you get to assume it starts at 1. And so this would be 2 plus 3n over n squared. So this is 2 plus 3 times 1 over 1 squared, plus 2 times 3 times 2. Whoops, 2 plus 3 times 2 over 2 squared, plus 2 plus 3 times 3 over 3 squared, plus 2 times 2 plus 3 times 4 over 4 squared. And when you add all of those up, we end up with 7 plus 2 plus 7 over 72, or 9 plus 7 over 72, which gives us 655 over 72, if I've used my calculator correctly. So, I have a couple practice problems here. As usual, please pause the video and try these out. So find the third partial sum of series from I equals 1 to infinity of I plus 3 over 2i, and B, find the fifth partial sum of the sum, let's do this one, of a sub n equals n plus 2 over 3 if n begins at 0. I want this to be the 6th, so make that switch. So the 6th partial sum. So, like I said, pause the video, try these out. I'll start going through the solutions now. So part A, we're doing the 3rd partial sum. So we're doing S3, which is the sum from I equals 1 to 3. So I plus 3 over 2I. This is 1 plus 3 over 2 times 1, plus 2 plus 3 over 2 times 3. 2 times 3, 2 times 2, plus 3 plus 3. Now it's 2 times 3. And when you add all that up, you should get 17/4. Now part B, try to trick you just a little bit here. So the 6th partial sum beginning at 0, that's S6, the sum from n equals 0. Now the 6th partial sum, if we start at 0, only counts up to 5. So that's why we have to be careful when we have these restrictions. The first 6 terms when we start at 0 are 0, 1, 2, 3, 4, 5 of n plus 2 over 3. So that's going to be 0 plus 2 over 3 plus 1 plus 2 over 3 plus 2 plus 2 over 3 plus 3 plus 2 over 3 plus 4 plus 2 over 3 plus 5 plus 2 over 3. When you add all that up, you should get, if my math is correct, 9. So partial sums just give us a way to talk about series in a more manageable fashion. The last thing I want to talk about is writing series in summation notation. So we get a lot of practice evaluating series, but let's say we're told to write the given series in summation notation. And our series is 3 plus 6 plus 9 plus 12 plus 15 plus ... So, in case you needed another reason, this is one of the other big reasons that series and sequences get taught at the same time and are so easy to confuse, because there's no difference between this and finding the general term of a sequence with the same numbers. So when you're finding summation notation, we want the sum from I equals 1 to k of a sub n. Well, this a sub n is the general term of either the series that we're thinking of as a series, or it's the general term for the what we call associated sequence. So there's no difference between what we did in 14.1 and 14.2 and this. So we're looking at these terms. We can see that we add 3, add 3, add 3, add 3. So my guess is that a sub n equals 3n. Now again, we're going to assume that we start at 1 unless we're told otherwise. So that means our sequence, since we have the ... here, this tells me that it's an infinite sequence. So we're going to go from I equals 1 to infinity of 3i. Oh. Something I've been doing, I think I did it a couple times. Your variable in your index should match the inside here. So if you use n in here, use it down here. It's not a huge deal, but as we do it. So that's the nice thing about this half of the section is when you're told to write something in summation notation, it's the same thing we were doing in the last two sections when we're writing the general term of a sequence. So nothing new to learn there. It's just about seeing it with pluses instead of commas. And if you feel better about it, you can switch it to commas like I did. But that is the end of 14.3.